We're going to talk about strong and weak acids in this video, and the first thing we need to do is home in on these words strong and weak and find out what they mean, because they mean something slightly, quite a lot different than they would mean in everyday life. So in everyday life, you've got two glasses of orange squash here. We'd say that this one was like strong. We might say this one is weak. You've got to stop using those words now, because rather than calling it, we have to say this one is concentrated, not strong, and this one is dilute, because those words strong and weak mean something completely different when we're talking about acids. Okay, so let's think about hydrochloric acid first of all. Right, we've got HCl, which is a strong acid, and we know that acids, when you put them into water, they dissociate into ions, so they become an H plus ion and a Cl minus ion. All right, so we'll draw a little diagram for that. I'm going to draw, okay, that is the HCl covalent molecule, and when you put it into water, it's going to dissolve and it will dissociate, so you're going to get an H plus ion. They separate away from each other, and so that leaves a negative charge on the chloride, and they are floating around in solution completely separate from each other. Right, this is a strong acid, so that means 100% of the molecules actually do that. All of them will dissociate. Now let's think about a weak acid, and probably the best example, of the most common example of a weak acid would be ethanoic acid. Ethanoic acid has got this formula, and it's in vinegar, so solutions of ethanoic acid smell of vinegar. Right, they dissolve, but I'm going to draw a reversible arrow this time. That will dissociate and it will form H plus ions again, and this time it will form the ethanoate ion. We don't really need to worry about the formula, but it's going to be just that, CH3COO minus. And I'm going to draw that one as a, like this. I'm going to draw, so that's the ethanoate bit, and that's the hydrogen covalently attached to it. It's this hydrogen is covalently attached, and when you dissolve it in water, some of it dissociates to form H plus, and this will be the ethanoate ion, which is drawn blue with a negative charge on it. But with weak acids, it's only about, well, it's only a small proportion of the molecules that you do that. With ethanoic acid, it's about 1 in 100 of the molecules will dissociate to form H plus. The rest of them will just stay like that. Okay, so let's look at some diagrams to see that a bit more visually. Okay, so what I've got here, this is our hydrochloric acid, HCl, and you can see 100% has dissociated or ionized. So you can see that, look, all of it is that every single molecule has split up into an H plus ion, that red bit there, the plus, and the chloride ion there, which is a minus. And I've actually drawn one there which is not split up, because of course you will get the odd one that doesn't, but all intents and purposes it is 100%. Now this is ethanoic acid, and weak acid, CH3COOH, and only about 1 in 100 molecules dissociate. So you can see that most of it is just the hydrogen covalently bonded to the blue ethanoate ion, but occasionally you do get one like that one there. It splits up to form a hydrogen ion, and there's the negative ion that goes with it, and there's another positive hydrogen ion and another. Okay, so you can see there then, if you had two solutions of HCl and ethanoic acid of the same concentration, so let's say that they're both a concentration of 1 mole per decimeter cubed, so the same concentration, the hydrogen ion concentration in this one is going to be 100 times bigger than the hydrogen ion concentration in this one. And that. Okay, so the hydrogen ion concentration in the strong acid is much stronger. And if you remember what the pH scale. So I'll just move this down a little bit. Well, if, for example, it's turned out that this HCl had a pH of 1, which would be about right, the ethanoic acid, because it's 100 times weaker, the pH scale is, remember, it's called a logarithmic scale. The pH scale would be, it would be 2 bigger, so that would be pH 3. Okay, now because if you've got an increase of 2 pH units, which doesn't seem much, but it's actually that means that refers to a 10 to the power of 2 change in concentration of hydrogen ions. So pH 3 only sounds a bit weaker than pH 1, but it's not. It's 100 times weaker. Okay, so it's going to be less good at doing the things that acids do than hydrochloric acid. Of course, you could tell by adding universal indicator. If you put it in hydrochloric acid, it would go red, showing it's pH 1. If you put it in ethanoic acid, it would be more of an orange color, showing that it's about pH 3. So yeah, it's 100 times weaker. So let's talk about the sort of things that acids do. Well, acids dissolve reactive metals. Okay, so I've got a tube here. I'm going to put magnesium in there and hydrochloric acid, and that's going to form magnesium chloride, and it will form hydrogen gas. Magnesium chloride is an aqueous solution. That's of course aqueous solution, and the magnesium is solid. So what we'll see here is first of all we'll see very fast fizzing, and we'll see the magnesium dissolve. Now, in the case of, if you put a piece of magnesium ribbon into 1 mole per decimeter cubed HCl, it dissolves in about 15 seconds. Very, very quickly, it's gone, and it fizzes rapidly. Magnesium dissolves. Let's see what happens when we put it into ethanoic acid here. So this is ethanoic acid, weak acid. So the hydrogen ion concentration, even though the acids are the same concentration, the hydrogen ion concentration is going to be 100 times weaker in this one. So the reaction is going to be way slower. So this is a very similar reaction. You get magnesium, and you get, don't worry about the, right? To balance that, we have to put a 2 there. It's the same here. We have to put a 2 there, and we're going to get magnesium ethanoate, which is, don't worry about the formula of that, but that's what it is. And you're going to get hydrogen gas, which you can see. So the magnesium, that's solid. This is an aqueous solution. Same thing happens. Magnesium dissolves, and you get hydrogen gas. But in this case, the acid will take about 100 times longer for it to react, because it's much weaker, and the amount of bubbling is far less intense because the acid is so much more dilute. So finally, when we're talking about weak and strong acids, we mustn't confuse those words with concentrated and dilute. They do not mean the same things. Got them the wrong way around. Okay, that one does not mean weak, and that one does not mean concentrated. Okay, we'll leave that one there.